Hello radiation nerds, this is your typical radiation survey meter, capable of measuring radiation with scintillators and Geiger-Müller tubes. Today I want to show you how, using a very cheap upgrade that is basically just an Arduino, we're gonna be able to improve the performance of this meter, enhancing the capabilities like adding remote measurement via Wi-Fi and most importantly enabling a digitalization of the impulses so that we can unlock a digital scaler and ratemeter. It is an instrument that usually much more expensive than this analog version. But before proceeding to show you how I modified it, let's briefly talk about what is a survey meter and how it works. So this is basically all that's to it. An analog display that has a count per minute unit. So this shows you how many impulses the probe is sending to the meter. The probe is connected via BNC here, and in this case I'm using an X-ray gamma probe. Other probes like Geiger-Müller tubes can be used, and this is the cable used to connect the two. To turn it on, we have the usual dial here that has different numbers, meaning the multiplication factor of what you read on the scale. And here on the left we have some controls like turning on and off the audio, the integration speed, zeroing, and battery check. So this is pretty standard and kinda boring, because with this we can just measure the instantaneous count rate and nothing else. But by implementing this little board that I made with just an Arduino and a couple of components that I will be showing you later in more details, you can see that we can now access a lot of more possibilities. So let's now install it on the meter itself. It's very simple, just need 3 connectors, 1 for the signal and 2 for the power. So we can go ahead and lift this part of the meter. I disconnect the probe from the meter. We simply take the power and the ground from the battery so that we can power our electronics using the internal batteries and don't need any other stuff. And then we can just place this little board inside of a free space. I'm gonna cover it with some tape to avoid shorting it to other parts. So after putting it inside, we now connect the signal cable that I will explain in more details later, and after tidying up a little bit the connections, and then we can close it. So let's now see how this practically works. So we take our phone or any other device and turn the meter on like usual. We hear it screaming as usual, so I turn the audio off. And let's turn on our Wi-Fi. Okay, we see that now this Wi-Fi here just appeared. Okay, now that it has connected, we can go over to our browser and enter the right IP address, and it will bring us over the page where it shows the data of the meter in real time. So here it's pretty easy. Any one of you can modify this interface very easily. It's just an Arduino code. The reason I'm using Wi-Fi and not Bluetooth is that for Bluetooth to work I would need to make an application just for this, and it would be very complicated and have problems interfacing with other devices like a computer and other phones. And also Bluetooth is, my experience, less reliable than the Wi-Fi, so I decided to host on the ESP32 the Wi-Fi server, so that any device can connect to it and see the same thing without any proprietary application. So here we see the live count rate. You can see it matches the one shown on the meter, but it's more precise, of course, because this is all digitalized. We can change the integration time, for example, to have a slower or faster response, like we do on this analog part. And we can also change from CPM to CPS, so count per second. But the most interesting part, in my opinion, and to show you this, I'll switch over to the computer as it's bigger. We can see that we can use it as a scaler or a rate meter. So here on the phone, but this works also on the computer, we can, for example, press start, and as you can see, the scaler start counting. This is now live counting exactly every single pulse that the meter is receiving from the probe and adding it up to the previous one. And why this is important? This is an important capability that usually it's only more expensive meter have, and it's important because with the right probe it allows you to check for contamination, for having a more precise measurement. With a usual meter we can just measure the instantaneous rate at which the pulses come from the radioactive decay around us. These pulses are measured on a very short time interval, for example 3 seconds or 12 seconds, but by using the scaler, so counting every pulses in an interval of time that we decide, we can have a very more precise measurement, because the error over the measurement is bigger the shorter time window you use. Why this matter? Because this allows us to measure contamination with the right probe. For example, if we take our probe and place it over a contaminated surface, maybe an alpha sensitive probe, we can now use the scaler to assess how badly contaminated it is. Maybe our surface has a little bit of contamination, but this amount of contamination is not big enough to show on the analog meter, because maybe the fluctuation that it naturally have of the dial are just too big to see a very small increase that might be present due to some alpha emitting substances. So what we do, we increase the measurement time using the scaler, and so we can now measure a lot more of alpha impulses in a bigger time, and then we can take also a background reading without the alpha emitting nuclide, for example by placing a sheet of paper between the surface and the detector. And if we use a long enough integration time, so this here, if we let it go maybe for an hour, maybe 10 minutes, it depends, and then calculate the number of pulses measured with and without the background, we're gonna be able to see an increase if contamination is present. This increase could not have been seen without a scaler, because as I said, the deflection of the needle due to the alpha particle in case of a low concentration might be too small to be detectable, as the error on the reading, on the instantaneous reading, is much bigger. For this reason, this very cheap upgrade could be a very nice improvement to your survey meter. Another useful thing that is capable to do is, of course, show us the data remotely. As you can see, I can see the count rate digitally from my phone or the computer or anywhere where the Wi-Fi signal reaches. And so I can, for example, set up radiation monitoring station that might be the meter that is kept on running for long periods of time, and can send the signal to my computer where they are stored, for example to monitor the presence of contamination in the air or other places. Also, this allows for much more precise measurement in case of a very high count rate. Let's for example take this radioactive rock. If I place my probe near it and I see the increase in count rate, using the standard analog meter, I will not be able to measure very precisely, because I know that it's around 250,000 counts per minute, but that's it, because I don't have the decimal point, because my meter is not counting every single pulses. With instead my digital version, I can see much more precisely my count rate in CPS or CPM up to the last digit, because again we are counting every single pulses this time. So this is the main demonstration of the device. Now, if you are interested, I will show you how it is made. It's a very simple circuit, so let's go. So this is the little board that we are using. It's mainly an Arduino ESP32 Nano. Chose this because it's small, it has good Wi-Fi capabilities, and has a pulse counter unit, and a 5-volt boost converter and a comparator. I will show you those shortly. But before, let's see how it works, because how can we transform this analog rate meter into a digital signal? Well, most of these meters get the signal from the probe, that might be a Geiger counter or a scintillator, through the high voltage on the BNC, then decouple the pulse itself from the high voltage using some capacitors, and then transform that pulse into some square pulses that are then used with other electronics to power this dial and show us the instantaneous rate, so count per minute or counts per second. But if we tap correctly on the board with just one cable, we can intercept that square pulse that is created inside of the electronics of the counter for every radiation event that it measures. If we are, for example, on the 1x scale, our maximum rate will be 500 count per minute, and so the pulses can be very long in time, for example 1 millisecond or a bit less. If we're instead on the 500k counts per minute, to fit all the pulses in 1 second, the single square need to be much shorter, and now they might be, for example, 10 microseconds. But anyway, this is still fast enough for our Arduino counting unit, and that's why we can do all of this. Let's return to the main schematic. So we have the 3 volt coming from the meter battery, powering this 5-volt converter unit. This then powers this voltage divider that makes a 0.45 volt as a reference voltage for the comparator, and the 5 volts directly power the comparator. Signal from the scope that we tapped on the board, in this case for this Johnson GSM 15 survey meter, it's very easy, as it can be tapped from the output jack here, that is hidden inside there. But I'm pretty sure that in other meters there is the same possibility. You just need to look a bit on the board and find the exact pin where you can place your cable and just take the signal out. The signal from the meter that we tapped from the board is pretty small. This is a problem because it is 900 millivolt, and this is not good because our Arduino cannot read it. So that's why we need our comparator. The comparator takes the signal from the pulses, the square signal, and compares it to the voltage level, 0.45 volts, and is connected to the Arduino analog pin 3. This is where the PCNT unit, so pulse counter unit or timer, on this Arduino is connected. It is, I don't remember how much, maybe 12 bits, so we can count a lot of events. Anyway, this pin, analog 3, is pulled up to 3 volt by a 10k resistor. Why? Because this comparator can just pull our output to ground. So what basically happens is that from the signal pin it enters some pulses every time a radiation event is occurred. These pulses are 900 millivolt in height. Meanwhile, on the pin analog 3 of the Arduino, this is happening. There is a constant 3.3 volt applied, constant voltage, that is there because of the 10k pull-up resistor. When a pulse comes in, it triggers the comparator pulls the collector output to ground, and so it pulls our analog 3 to ground. This keeps it grounded for the length of the radiation pulse until there is no more pulse over here, and so this turns back on 3 volts. This goes on until it detects another pulse and goes on again. So we see that we are basically inverted these pulses, but we inverted them with a much bigger voltage of 3.3 volts that can now be detected by the Arduino. It doesn't matter if the pulses are positive or negative at the end, because the pulse counting unit can detect both the rising and falling edge of our pulses, and so you can see either end of the pulses and count it anyway without any problems. Pulse counting unit is refreshed every 0.5 seconds. So why? Inside the Arduino there is two parts of code. One code is used to run the web server that displays the data on the Wi-Fi. So the Arduino is basically a host of Wi-Fi that anyone can connect to it. It has a password, of course, so you need to know the password, and it can host this server, and you can connect to it with any device that has Wi-Fi capabilities. Then you go on the browser that you choose and insert the right address, and it will connect to this page, which is the page where the data is shown. This is one part. The other part is the counting. So this occurs in the following way. Every 0.5 seconds the buffer of the pulse counting unit is read by the Arduino, and so this basically read how many pulses has been recorded in this 0.5 seconds. It might be 10,000 or whatever the radiation around you is doing. It now eliminate the data from the buffer, and so it reset it. We could even leave it right there, but after a bit of time it will overflow. So why this approach is very good? Because we can run the server and in the same time measure the number of pulses without losing any pulse. The reason is because the pulse counting unit on the Arduino keeps working and counting the pulses in a completely independent way from what the processor of the microcontroller is doing. So even if the Arduino is doing 1,000 things at the same time and might take 1 second of time because it's very busy, we will not lose any pulse because the pulse counting unit works completely on its own. This is a different approach. For example, if we fed the signal to a digital pins where the Arduino was just waiting for a trigger event and count it, and then do the other web part simultaneously, because in that case, when the Arduino is doing his other part, for example displaying the data on the web, it will be no longer available for counting the pulses that are coming. But this is not the case using a proper counting unit. And so with this approach, we now calculate the rate by dividing how many pulses we got in the time interval. By the way, this time interval can be varied. You just need to change a number on the code. And then the Arduino also vary the integration time, the averaging, sorry, that you can see here. That is the 3 second, 6 second or 12 second, just by making the average of 6 time interval of 0.6 or 12 time interval or 24 time interval, and this changes how fast it will respond to a radiation changing in the ambient. So if you have a very short averaging time of 3 seconds and you bring a rock close, it will go up instantly. If you instead have 12 seconds, it will need more time. Why we use this? Because with 12 seconds there is less fluctuation in the number. So this is it. Everything is on this little board. We can sandwich it together, put it inside a space that is present here on the meter, and it works quite well. The main point of force of this, in my opinion, is the fact that you can use it as a scaler, and so measure even low activity stuff or contamination. So if you're interested in building something like this, it costs very little. Let me know. I can give you the code running on the Arduino without any problem. It has been written mainly using AI, so I can give you it away. Let me know in the comments if you want it, and if you have any question, let me know also that in the comments, and bye bye.